So today the topic is applications of conductance. Applications of conductance. Okay. So first applications is that is on dissociation constant. On dissociation constant. So dissociation constant, that is alpha equal to molar conductance at any dilutions at any concentration by molar conductance at infinite dilutions. And this, and we know this alpha how it is related to this molar conductance and molar. So dissociation constant how it is related to this. So let's search. If we have weak acid, any weak acid or weak base, then this is partially dissociate. And let's say T equal to 0, let's say this is C concentration 0 0, and let's say T equal to T equilibrium, this is become C alpha dissociate, C alpha, then C minus C alpha. So Kd equal to, for equilibrium constant, and here for dissociation you are doing, so K equilibrium equal to K dissociation constant, that is product by concentrations. So product is CH3, CO minus and H plus upon reactants, that is CH3 COH. So Kd is equal to C alpha, C minus C alpha. So this will going to become C square alpha square, then this is C 1 minus alpha. So this cancel, then Kd we get C alpha square 1 minus alpha. Okay, that is K dissociation equal to C alpha square 1 minus alpha, and this alpha is equal to molar conductance at any concentration upon molar conductance at infinite dilutions, this alpha. Okay, so this is the relationship. So this is the applications of conductance on dissociation constant. So if dissociation constant we know, then we can calculate the alpha, and alpha is related with molar conductance. Okay, this is the first application. So we will solve the more problems, then it will be more clear. So this is on dissociation constant, first application. And second applications is solubility and solubility product. So how? Let's say so we already discussed in ionic equilibrium about solubility and solubility product. So let little bit recap that. Let's say for any weak acid, so here that same things wherever in that weak acid, weak base, or that ionic dissociation constant there is study, here you will same thing you will study, but in a different way, that is sparingly soluble salt, another is completely soluble salt. So another is, one is completely soluble salts, another is sparingly soluble salt, sparingly soluble salt. So this completely soluble salt we can compare with strong acids or strong electrolytes, and this sparingly soluble salt we can consider as weak electrolytes. So same concept as we studied in strong acid, strong electrolyte and weak electrolyte, same concept here also we will study about solubility and solubility product. Okay, so here the completely soluble salt, like for weak strong acid NaCl, strong electrolyte NaCl, NaOH, all that are comes in strong electrolytes which are completely dissociated. Similar case here, completely soluble salts that will comes. So I'll just erase this. Completely soluble salts are examples like all compounds of nitrates, or we can say compounds of, let's say what, like K plus, Na plus, NH plus, let's say Cgm plus. So all these compounds of this are sodium plus. So this type of compounds, if the compounds having these elements, then they are called as completely soluble salts. For this, solubility and solubility product we will not calculate. Solubility and solubility product we will not calculate. Similar, like we say NaCl, NaOH, HCl, or strong electrolyte, we will not calculate that K equilibrium. We will not calculate the alpha. So similarly, here also we will not calculate solubility and we will not calculate solubility product. Here solubility product we can take as this alpha. So here this alpha we are saying S, and here equilibrium constant we are saying KSP. Okay, that things we can relate it with this strong electrolytes, weak electrolyte, like that, completely soluble salt and sparingly soluble salts. So here this we will not calculate. So where we calculate, that is sparingly soluble salts. Sparingly soluble salts. What are sparingly soluble salts? Compounds like AgCl, AgBr, AlCl3, like that compounds. Okay. So many more compounds. So that compounds, for this case we will find that KSP, S below, S is solubility, this KSP is solubility product. Similar, like strong weak acid we are saying this is alpha, this is we are saying K equilibrium. So similar way we can compare that. Okay. So let me calculate with one examples we will do. Okay. So one examples, let's say AgCl. So also we know that type of sparingly soluble salts, they have types of sparingly soluble salts, like we have 1:1, like AgCl, or I can write AB type, like we say AgCl, AgBr, like that. And we also have 1:2, like AB2, and we have 1:3, like AB3, and we have 2:3, like A2B3. So variety types of sparingly soluble salts we can get. Okay. So let's find that KSP value. How will you calculate? So same case as like we studied weak acids, how we will calculate the K equilibrium constant the similar way. Like, so you say that AgCl, then this is, so this is solids. So these solids will partially dissolve, not completely dissolve. So this AgCl aqueous will be very less amount, like CH3COH. This is partially dissociate. Okay, since this is 1 molar, then 0.01 molar, 0.01 molar, like that, very less dissociate. Similarly, where this will partially dissociate. Let's say here high amount is there, 1 molar is there, then this will dissociate in very less, that is 0.01 molar dissolve. Okay, and since this is a strong electrolyte, so this will completely dissociate. So Ag plus Cl minus. Okay, this is at T equal to 0, and if T equal to saturation time, means after that no more dissolvage occur, that is called saturation time. For acids, what are saying that if we say CH3CO minus plus H plus, T equal to 0, this is, let's say C 0 0, T equal to T equilibrium, where no more dissociation happen. So for this case T equal to saturation time, where no more dissolvation happen, here where no more dissociation happen. Okay, on that time this is, since very less dissociate, so this value is again here as left in so many means huge amount of compounds this left, this is very less dissociate. So here very huge amount, like 0.99 molar is left, and this is this amount is dissociate. But this is a strong electrolyte, so what happened, this completely, whatever the dissolve have, this is completely dissociated. So this become 0.107, 0.01, 0.01, because this is strong neutral act. Okay, but so this is from here the dissolve is less, but whatever the dissolve, that will completely dissociate, because this is strong neutral act. Like Cl comes from HCl. So HCl is strong acid. So if any compounds come from strong components, that salt is known as strong electrolyte. So this is strong electrolyte. So this is Ag plus Al minus. Okay. So at saturation time, what is present? This is present. So we say that whatever the present in equilibrium, that we use in K equilibrium, that is C alpha into C alpha equal to C minus C alpha, used to do like that. Similarly here, whatever in the saturation time, that we will calculate, because actual compound this is present. What is present in saturation, that is what we get in the solution. So here if we find that K equilibrium, so this K equilibrium we call here as KSP, because we are doing the solubility. So if we find that solubility product, okay, that is equal to product. Let me do in other pen. That will be, sorry, so KSP. Here the K equilibrium, here you call KSP, that is equal to concentration of product, this upon concentration of reactants. So this is not left, so this we will not use, because in the saturation time this is not left. So whichever left, that we will calculate, right? So this and this, so this is AgCl solid concentration, and solid with respect to aqueous is termed as 1, because this is very huge amount with respect to aqueous. So this is considered as 1. Or also we say that this quantity, this concentration is very huge amount compared to this, so we consider this as 1, not dissociate. Okay, so this considered as 1. Okay, then what we find, that KSP equal to Ag plus and Cl minus. And if we are doing that solubility, so if I says that this concentration is S, if Ag plus concentration equal to Cl minus concentration equal to, if I says S concentration is there, or S amount of solubility is happened, then KSP will equal to what? S into S, that is KSP equal to S square. Okay, so any problem from here? Because this and this concentrations I am taking as S and S, so this is become unit 1, so only this is left, so I am taking this and this as S. We can take A, we can take B, we can take C, any value, but since we are talking about of the solubility, so we will take that. They given the scientists first, they give that this, let's say this is S, because this is for solubility, so they put the S. So if they put S, then this is S, this is S, because whatever is there, that is equally dissociate. If initiality 0 0, if initially some amount of this is present, then this may be differ, but initially this is same, then this is become same. Okay, so KSP is equal to, so KSP is equal to S square. So now the question is, we are studying here the applications of conductance. So I have discussed that molar conductance is equal to what we have discussed, that is conductance, specific conductance upon molarity, and we know that molarity is equal to concentration. So molarity and concentration is same, because molarity is number of moles upon volume in liter. Same concentration also same, number of moles in volume in liter. So I can write C equal to M. So here you can put any value, C or M, any value. So I put here C. So this is concentration and its unit is moles liter inverse. And this S, if you see that this unit of solubility also, this is also a concentration, because this unit also mole liter inverse, same unit as concentration. So what I say is that C equal to S, because this is also concentration, this is also concentration, because for solubility also using that same concentration. So C is equal to S. Only the problem is that whenever you are finding KSP, for KSP its units is always taken in moles. So if the concentration unit is other than in moles per liter, then we have to change the concentration in moles per liter inverse, then only we will put that. For S, we see KSP equal to S square, then S equal to KSP upon 1 by 2. So here from we find that S value, but putting the KSP value has to be unit in mole liter inverse. So before finding that, before putting that concentration, be sure that unit of this, unit of S should be in moles liter inverse. Okay, so here C equal to S we says, then from here I can say that this molar conductance is equal to K upon S. Okay, and this S comes from where? We can find from here that S equal to KSP upon S equal to KSP upon 1 by 2. So KSP, by using solubility product, we will find that S value, because S equal to KSP upon KSP under root. So we will put that S value here, then we will find that is equal to K upon KSP 1 by 2. Okay, so this is the applications of conductance in solubility and solubility product. And one more thing, note that we know that K of salt plus K of water equal to K of solutions. This we know. And if in questions, if in question K of water is not given, so in question sometimes K of water is not given, then what we say that K of salt equal to K of solutions. If K of water is not given in the questions, then simply do that K of salt equal to K of solutions. No need to worry about of K of water. If not given, then simply avoid it. Take that K of salt equal to K of solutions. And this is the one case. Second case, if in questions K of water is given to you, K of water is given, then K of water is given, and they ask that K of salt or K of solution also given to you. K of solution is also given to you, and ask that K of salt is how much. They ask K of salt. Then on that case, what you will do? Since we know, because K of salt plus K of water equal to K of solutions. So K of salt will be how much? K of solutions minus K of water. Because K of solution is given and K of water is given. So let's say K of water is x1 and K of solution is, let's say, x2. Then K of salt is K of solution is x2, then x2 minus x1. Okay, like that you have to find it. And another case, like if K of salt is given to you, if K of salt is given to you, given, also K of solution is given, then ask that K of water is how much. Then what you will do? So if K of salt is given, let's say K of salt is x1 and K of solution is, let's say, x2, then what happened? Where they ask that K of water is how much. So you know K of salt plus K of water equal to K of solutions. So K of water is K of solutions minus K of water, and K of solution is how much? Let's say x2, and K of water is x1. K of K of salt, sorry, this is K of salt now. K of salt, so K of salt is x1, so like this. This is the K of water. Okay, like this we can calculate. And the third, this is how much? Third applications is very important, that is conductometric titrations. Third applications is conductometric titrations. Conductometric titrations. This topic. So what do we mean by conductometric titration? What are the principles? Principle is very simple. We are adding that one ions, and that is we are replacing of one ions with another ions, and after that results of when we replace, after that after replacement, another new ion set comes with new ions, and with present ions, what is the result in the what is the result in that? Actually we will stop from here because there is a